Well, it's been a long while since I've done a physics video, but since it's minus 10 outside and wind chill of minus 39 in Marion, Indiana, I think I can take the time. This is from Young and Friedman's University Physics. We're in the chapter on Gauss's law. This is the second section on calculating electric flux or electric flow, as it were, as a metaphor. So this is what we got kind of from the previous section, the first section of this chapter. Qualitatively, we can express Gauss's law in this way. The net electric flux through a closed surface is directly proportional to the net charge inside that surface. Doesn't matter what kind of surface you're talking about. As you'll see in the examples in this section, could be a sphere, could be a box, could be a cube, could be a diddly-blah, whatever that is. But basically, the amount of flow of electric flux, as it were, coming out of that space, that surface, is directly proportional to the net charge inside. It took James Clerk Maxwell and building on the work of Michael Faraday, took him ages to figure this out. Man, if he could only read this, if he could only watch this video, James Clerk Maxwell, how much further ahead he'd be. But anyway, basically he compared electricity to fluid flow. And this was the analogy that helped. Now, it's not a fluid flow. This is just an analogy, but it helped. It was a mental model that helped him figure out the math of it. So if you remember back in chapter 14, I don't, but if you do, back in chapter 14 of University Physics, we learned that the dV dt, that is the instantaneous rate of change of volume in a flowing water or liquid, is the velocity of the liquid times the area it's passing through. So if you want to know how the change in volume is happening in relation to time at a particular spot in a three-dimensional flow of water or liquid, it's the velocity of that liquid times the area it's passing through, and perpendicular area. It has to be perpendicular. So this is from way back in chapter 14. Why does it work? Well, I'm not sure why this works, but what I know is that the units work out, and that helps me. So miles per second, or not miles, meters per second is velocity. Area is meters squared. It's two-dimensional, right? If you multiply that out, you get meters cubed per second. Well, that's volume, right? Volume is meters cubed. It's three-dimensional. So the units work out. So I believe the powers that be when they tell me that dV dt equals V times A. All right, so here's an example of that to picture it. These drawings have been written by none other than me. I know you're surprised that such good drawings could come from me. But basically, let's say we've got a fluid flowing through a particular area, perpendicular. This is the velocity. It's a vector. That means it has direction as well as magnitude. So the instantaneous rate of change of the volume per time equals that velocity times that area. Okay, great. Now, here's a slight problem. What if the area we're looking at is not perpendicular? And here, basically, we have to find the perpendicular. So if the area in between the surface it's going through and the perpendicular, we'll call it phi. So the cosine of phi is basically the adjacent side over the hypotenuse, right? So if we multiply by the hypotenuse, which is the area A, then if we multiply the area times the cosine of that angle, we're going to get the measurement of this, the perpendicular. Now we have the perpendicular, we can apply the formula we had on the previous page. So dV dt equals the area times the velocity times the cosine of that angle, phi. All right, here we have it down here. Now you may remember from way back in the very first chapter of University Physics, you might not, that the dot product of two vectors is basically this. It's the first one times the second one times the cosine of the angle between them. And so another way to express this is the vector velocity dot the area. And the area, of course, can change as well. Well, that's all really review of chapter 14. But what James Clerk Maxwell did is he applied this to electric flux. And so we can basically say that phi sub E, that is the electric, so flux, and the Greek letter phi, actually, but we call it phi in science, is so flux. Flux starts with anyway. So flux sub E equals the E, which is like the velocity, times the area it's going through. Okay, so it's exactly analogous. The flux, electric flux, phi sub E, equals E, quantity, times A, the area. All right, and we can therefore say that when the surface we're talking about isn't perpendicular, then it's area times that field times the cosine of phi, which is the angle between the perpendicular and whatever the surface is. And we can also call that the dot product, that the flux, electric flux, is the vector E dot vector A. What's the vector, Victor? So this is for a flat surface in a uniform electric field, okay, where E is the field, right? Electric field. Coulomb's law stuff. Okay, so what if it's a variable electric field? Well, then we're going to use integral calculus. And we're going to say that for every infinitesimal bit of area, d vector A, dot product, the electric field, the integral of all that, you add up all the little, this area, 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 that's going to equal what the flux is. Now, this is not so important for this video, but as we get to the full expression of Gauss's law, we can say that A vector n is something you need to know. N is called the normal. It is the perpendicular to the surface. So it's a unit of 1. So vector n is basically a way of saying we're talking about the perpendicular to the surface. So vector n, or normal vector, is basically saying the perpendicular to the surface at every point. Anyway, that's not so important in this video. It's a commercial for later videos. Just kind of tuck that away. You'll know what that's about later. Don't worry if you don't understand that now. You'll know soon enough. So another way of expressing this is that the electric flux, phi sub E, equals the integral of the perpendicular to the electric field for every infinitesimal A. And as we've said, you can also put it in this form: phi sub E equals the integral of E cosine phi dA when it's not perpendicular to it. This is called a surface integral. We're going to be talking about surface integrals. There's actually a symbol for it. It has a little circle in the middle of this wonky S of the integral. So if you have a little circle around there, that's another way of symbolizing a surface integral. But it basically means we're adding up the surface. So surface of a box, surface of a sphere, like I said, it doesn't matter what the charge is enclosed in. We're taking the total of all of the infinitesimals of the field times the area all around whatever the surface is. So it's called a surface integral. I think I'm done. Yeah, we're done. So this has been a video trying to move toward a quantitative way of talking about flux. And what is this Gauss's law qualitatively? It basically says that the net electric flux through a closed surface is directly proportional to the charge inside the surface. Hold that thought. We'll be back with more on Gauss's law.